There we go. All right. All right, so we have a kind of short one. Now, I did lie to you because I said we were going to do lecture 20, 21, and 22, and then take a test. I lied to you. We're not doing lecture 21. 22, though, is broken up in like 3 or 4 parts because we do exponential functions, we do log functions, and then we do properties of logs, all of that. So that's going to take us 2, 3, maybe 3.5 class periods to get through before our test. So we're still like 2 weeks away from the test. So just want to let you know. But we are starting lecture 22 because we did 20 the other day, right?
Mm.
And what was 20?
Rational functions.
Yeah. So lecture 17 was,
I forgot.
I believe it was quadratics.
Yeah,
Yeah, quadratic.
So lecture 22, so the big ones are linear, you learn in algebra 1. Quadratics, you typically learn in algebra 1, algebra 2. Learn a little bit of exponential. We're going to spend a little more time today talking about exponential functions. So today is going to be lecture 22, and if you want to call it part A, that's kind of what I did in my notes. Part A, we're going to talk about exponential functions, and then we're going to talk about logarithmic functions, and then how to solve those types of equations. So what is an exponential function?
Isn't it like the little curve on the graph? The little, that thing?
Yes.
Yeah.
Yeah. Looks kind of like a ramp. We have an exponential that then goes up.
Yeah.
Okay. Or if it's a decrease, it goes down. Okay. So like rationals, it does have a horizontal asymptote. Okay. Remember what's that? What's an asymptote?
When it gets closer to 0.
Okay. It's closer to a value. Typically this one's going to be 0, but closer to any value. It gets closer and closer without actually ever reaching that point. So they have, just like a rational has a horizontal and vertical, this has just a horizontal asymptote. Very good. Okay, so real quick, definition. Do you know what the definition or what the function looks like?
No, I forgot.
Remember?
Mm-mm.
No? Remember?
No.
All right, here you go. You don't have to write the whole thing, but here's the whole definition. It's an exponential function. Is a function with base b. It's going to look something like f of x equals b to the x power, or sometimes we could write it as y equals b to the x power, where b is a constant, positive constant. Positive constant other than 1. And then x is going to be an element of the real numbers. So we have base to the x power. So basically, if you want to kind of shorten that, the variable is in the exponent.
Mm.
It's when the variable is an exponent. So the base can be any number other than 1. Typically it's positive, so like 1 to the, or 2 to the 5th power, or 2 to the x power, 3 to the x power. And then x can be pretty much any real number, although we do look for positives. Because if it's negative, then we have another little issue with that. But typically we look at positives, we're going to look at most of that today.
Wait, what's always the positive constant? The b?
The b.
Okay.
Yes, the b is not going to be a negative value.
Okay.
So it's going to be 2, 3, 4, 5, 6. It's not going to be 1. Anything other than what could be fractions, it could be decimals. It cannot be 1. Why can it not be 1?
Because 1 times it's anything is just 1.
Yeah, it's a constant. 1 to any power, whatever x would be if x is to the 10th, 1 to the 10th power is 1. 1 to the 100th power is 1. 1 to the 1/2 power is 1. So it would just be a constant function, and we wouldn't have an exponential. Okay. All right, so some examples. Let's see here, some examples of what is. So obviously y equals 2 to the x. This, by the way, is what we call the parent function. If you ever see one as an example of an exponential, it's going to be y equals 2 to the x. We could have maybe f of x equals 3 to the x plus 1. That exponent could be an expression. In this case, the exponent is a linear function. So the exponent can be a function as long as it's in terms of x. Maybe we have g of x. This could be a fraction, 1/2 to the x power. Or even an expression, 2x minus 3, something like that. Those are all considered exponential. So what are not examples? Okay, well, things like -1 to the x power. A negative number to the x, it's not exponential. Why is that?
Because it's 1, it means 1.
Well, this one's case it's -1.
Even
Even if I had -2,
it will make it a positive.
well, it depends, right? I
Mm.
mean, just real quick, if x is 0, which is perfectly fine, what's -2 to the 0?
0.
Anything to the 0 power is
-2.
Oh,
1.
my fault. 1. Yeah.
1. If the exponent is 1, then it's going to be -2. If the exponent is 2, it's going to be
-4.
Positive 4.
positive
Yeah,
4.
+4.
If x is 3, it's going to be
8.
-8 now, because it's negative. And you're hopping back and forth between negative and positives, and it's just a mess.
So it's like inconstant.
Yeah, if you graph it, it looks really funny. Just like a
Okay.
bunch of dots back and forth.
Yeah.
Okay, so we can't have that. So the base, the b has to be greater than 0, but not 1. Any positive constant but 1. Okay, we also don't have this. This is x to the second. The base cannot be an exponent. I mean, that's a quadratic function. The base cannot be an exponent, and the exponent is not a constant. Okay. Or here's one that's kind of weird: x to the x power. That's also not an exponential. The exponent is a variable, but the base can't be.
Mm.
The base has to be a constant. Okay? So just some examples. We will need calculators. You got?
Yeah.
So let's look at the graph and some characteristics. All right. I was going to try and pull this in. Let's see if this will work.
There you go.
Trying something brand new. Import PDF. Well, that's not exactly what I wanted. I wanted the graph, but not like that. All right, forget it. We'll just sketch it on there. Okay, so first of all, let's do the graph. So whenever we do a graph, if we don't know what it looks like and you don't have a graphing calculator, what's the first thing we do? If you have no idea what a graph looks like,
Find the function.
we have the function.
Oh.
In this case, we're going to do a pretty basic one.
See
We're
where
gonna
x
do
and y is?
Whoops. We're going to do the parent function f of x equal x. Huh. Just wrote a non-function. Here we go. Equals 2 to the x. What'd you say? We're going to do what?
Find x and y.
We're going to plug in some points. If we don't know what the graph looks like, we're totally lost, we can at least plug in some points, get an idea. Okay, so let's plug in some points on this one. Okay, I'm gonna start in the middle, obviously, and let's go with, we can't have 1, but for x, let's plug in 0 for x. Okay, so if I plug in 0, I get 1, right?
Mm.
If I plug in 1, what do I get?
2.
2. If I plug in 2, I get
4.
4. Let's see how far did I go? I did 1 more. If I do 3, I get
8.
Okay, well, on this one, let's look at some negatives for x. Let's look at that exponent, let's make the exponent negative. What would happen if I put in -1 for x? What would 2 to the -1 be?
-2.
No. 2 to the negative first.
Why am I tripping out?
-2?
No. Remember, this negative here has nothing to do with this negative out here. What's that negative exponent tell us to do?
I completely forgot.
You in the back?
Would it be like 1/2?
Yes, because the negative tells
I
you to
got
move
that
it
right?
to the denominator, that becomes 1/2.
Oh.
Remember, that negative exponent's all about location.
Oh, I'm okay.
You're freaking calculus, you better get that one. Okay?
It's been a while.
Oh my heavens.
Can't
Okay,
remember
so
that.
what if I put in -2?
1/4.
Yeah. And -3?
1/8.
1/8. And if you notice, those are related. The 2's are related, the 3's, -3 and 3 are related. Okay? So let's go ahead and take those points. Let's graph them. Okay, so I'm gonna go 1, 2, 3, 1, 2, 3, 3. Change colors. Then graph those points 0, 1, 1, 2. I can't graph 2, 4, or 3, 8, they're off my graph. -1, 1/2. -2, 1/4. 1/8. So we see our graph that looks something like that. Okay, now, we did some numbers, we got to look what the graph looks like, we already kind of knew that's the shape of the graph. Give me its characteristics. Tell me everything you can about that function.
It never touches 0.
Okay, so it has an asymptote, right?
Yeah.
Can that asymptote ever be something other than 0?
Yes.
Yes, we can move it up, we can slide it up, we can do +1 and it slides the asymptote up.
Mm.
So by identifying where the asymptote is gonna be important. Okay, what else?
Multiples of 2.
They are multiples of 2, in this case, because it's multiples of the base. Okay, what else? It's something the quadratic has that this does not have. Remember, the quadratic function looks something like that, right?
Oh, medium and maximum.
Okay, so does this have a minimum or maximum?
I said medium. No.
Does this have a minimum or maximum?
I don't know. I think so.
What would be the minimum point on this one?
1/8.
Well, if I put in 4, -4, it's 1/16.
Yeah.
If I put in -5, it's 1/25.
Right.
So how low does it ever
0.
actually? Does it ever actually get to 0? So does it have a minimum value?
No.
No minimum. Does it have a maximum?
No.
No, because if I keep putting in numbers, it keeps getting bigger, right?
Right.
All right, so there's no min, no max.
And then
And what else does and that's kind of leading to the point, what does a quadratic have that this does not? What's the general name for a minimum maximum?
Vertex?
Vertex, doesn't have a vertex.
Okay.
There's no vertex to it. There's no turning point, if you will. Which means then, this is an important concept, this function is always, as I read from left to right, is always increasing.
Mm.
This is what we call an increasing function. It never turns around. It never decreases. It never plateaus. It constantly gets bigger the farther right you go. Decay would be the exact opposite. Decay would be coming down. Okay. All right, so asymptote definitely has one horizontal. I probably should put that in there. Has a horizontal asymptote.
Yeah, I was about to say that.
No min or max. It's increasing. What else?
Let's see. It's only in those two quadrants.
Okay. This one is only in quadrants 1 and 2.
Yeah. Wait, can it be in 3 and 4? Well, I guess it can.
Yes, if I subtracted like -4, then it would
Yeah.
slide it down and it would be down here.
Yeah. Okay.
So that's just for the parent graph, but it is limited to the number of quadrants it's in. Okay. This the parent function is. Okay, what else? Okay, answer this for me. What's this domain?
Not all real.
Okay, what real number can you not put into it?
1.
No, you can put 1 in. This base can't be 1, but I can put any number in for x. I can put 1 in for x.
Okay.
What number can I not put in for x?
0.
I can. It's 1.
2.
2. It's 4. What number can I not put here? Is there any?
No.
No. Domain is all reals.
Oh, it is all real.
Now, typically we like the positive ones because that gives us, easier to work with. But we can't go negatives. That gives us those fractions. Okay. What's the range? Took a quiz over this last year. What'd you say?
0 to infinity.
Okay, so in this case, it's 0 to infinity. Is the 0 a bracket or a parenthesis?
Parenthesis.
It's a parenthesis because it doesn't actually get to 0.
Yeah.
So what I'm going to put here is I'm going to put parenthesis and then I'm going to put the horizontal asymptote to infinity.
Oh, that's smart.
Whatever the horizontal asymptote happens to be. Because once again, we can shift this. In this case, it's 0, but we can shift it up or down. So it's the horizontal asymptote to infinity. Okay, let's see here. One other thing.
It does not have an x-intercept.
This one does not have an x-intercept.
Yes.
At most, how many x-intercepts would this have?
0.
1.
It would have at most 1. If I shifted it down, it could go like that and it would
Oh,
have 1.
yeah.
But remember, there's no turning point. It doesn't turn around at all, right?
Right.
So it has at most, I ran out of room. It has at most 1 x-intercept. But it could have 0.
Okay.
All right, very good. All right, let's go to this one. Let's talk about B. I don't know what to entitle this one. If B is greater than 1, like in our last case 2, we call that an exponential growth, right? Exponential growth. And that's the one that's always increasing, going up from left to right. Okay. What if B is between 0 and 1? We gotta be careful how we write it. Whoops.
Exponential decay.
It's exponential decay, yes. So if B is greater than or equal to 0 or less than 1, okay, now we have exponential decay. So like that example I gave you, 1/2 to the x power, that's going to be a decay. Kind of like, I think you said it, Cameron, because no one else has really been talking. Like the last one was multiples of 2, right? If it was 1/2, rather than doubling it, it would be cutting everything in half. So like 2 to the x, you said was multiples of 2, right?
Right.
That's doubling everything.
Oh, yeah.
Well, if it's 1/2, that means you're cutting everything in half.
Okay.
So, or if it was 1/3, cutting everything in thirds and going down by a third. So it's getting smaller and smaller.
Alright.
Okay. What can you tell me? This kind of be a new category. What can you tell me about the letter E? Because when we deal with exponentials and logarithms, we have this letter E in there. What is E? I think we just touched base on it last year.
Yeah.
Did you talk about it last year in Algebra 2?
Probably.
I don't remember what it was.
Nah. Can you give us a hint?
It's the base of a natural log. The definition is the base of a natural log. I am 100% sure that I taught Ellie this last year, but she does not remember it.
The what?
Do you remember how to compute E?
Like on a calculator?
Yes. No, how to compute it. Not like find it on a calculator, but to actually compute it. No, you don't.
No, I don't.
So I gave it to them last year, just like I'm giving it to you now.
Mm.
So in a year, I'll be sitting here with pre-calc class saying, I know I told Cameron this last year, but he's not gonna remember it. And he'll be saying things like on a calculator, and I'll say, no, like compute it, and you'll say, I don't know. All right, so here you go. It's the same thing every year, right? So here's how we find it. The limit as x approaches infinity, you've seen that before, right?
Yeah.
Okay, of 1 plus 1 over n to the nth power.
Oh, I remember that.
No, she doesn't.
Yeah, I do.
So,
That's what it equals.
oh,
We'll talk about the limits and what that concept is in May, and then of course
Yeah.
next year in calculus. But by definition, that's what it is. Now, do you remember the value of E? About what it equals?
1,
Not 1.
0.
No.
Dang it.
10.
No.
No, I
Do
thought
you remember
he was
about
right.
what it equals? Okay, it's kind of like pi, where it goes on forever with no repeating, no turn, no whatever like that. But it starts off with 2.71828.
Ah, yes, of course.
So it's
Yeah.
all just a little bit under 3. It's a little bit under 3. 2.71 is what we usually approximate it with.
We learned this?
You did not.
Oh, okay.
Well, I think I mentioned E, kind of what it is. This is more of a college algebra pre-calc topic. We kind of touched base on algebra 2, but that's about it.
Alright.
Okay, so that's what E equals. Now, we have this thing called logarithms, and this is going to be the base. So there are some applications for natural log. It shows up quite a bit in actual real life examples. So like a lot of times with population growth, doesn't have to necessarily be with people. Population growth is a great example of where we see this thing pop up. So let's give you an example. You have your calculators, right?
Yeah.
All right, so here's an example from the book. I like to steal examples from other math teachers. Sometimes I go to the book, and this was a good one from the book. So, the gray wolf. Do you
Wait,
spell
what are we-
gray with an A or an E?
Are we using graph?
An A?
Not yet.
Oh.
An A?
Yes.
What are we spelling?
The gray wolf, is it spelled with an A or an E?
An A.
It's an E.
She
It's
thinks
an
it's an
A.
A.
It's, no, the color gray.
You're not
Yeah.
biased at all.
C.
It's A.
I'm gonna put a question mark there, and you can spell it whichever way you want. The gray wolf in a certain region has a population modeled by, your book may actually tell you what it's, where it's at. It's modeled by the function f of x equals 1066 e to the 0.042 to the x power. Do you have any idea where they might get an equation like that?
From
Can I put this in my calculator?
Not yet. You can if you want, but we're not going to be there yet.
wait, so what is pop?
Population.
Oh.
So the gray wolf population is modeled by that particular function. Okay, so any idea where they might get that function? I don't think you've done
Like
it
in like
before.
real world times?
Yeah.
Oh, like, no, I don't.
You may have done it in some science classes. I know we haven't done it in math, but you can do what's called a regression line. So what you do is you take, have you done it before?
In Miss Young's class a little bit.
So you take all this data, all this information, you know, in this case, you would take year in population, year in population, year in population, and do it over, you know, several years, and then, or several decades even, and then you could take a formula, and actually Microsoft Excel or Google Sheets will create an equation for you.
I didn't know that.
You didn't know that? Okay.
Yep, I'm
So we
writing
came
that
up with
right
that
now.
equation, okay? So then it says predict the population in 12 years. So basically, all it's asking you to do is to find f of 12. So in your calculator, you're going to do 1066, and then you're actually going to use the button E. Okay, if you notice on your calculator, it's probably underneath or above the natural log function. It'll say ln.
Wait, so does E go first?
Yeah, so what you'll do is,
Oh, okay, I get it.
you'll do 1066 times, and then do you find the e to the x power? Did you find that button?
Yeah.
Okay, and then you'll put in e, and then you put in 0.042 times 12.
Wait, so 1066 times E. Where's E again?
Should be right
I got
there.
this big
Oh,
weird
okay.
number.
And to 0.042.
I got 1,000. Whoops.
111.726, or just
E to the
0.73.
0.042 times 12.
Nice.
I got 1,764.
Oh, I forgot to times it by 12.
0.58.
Oh, I did not get that.
Now, you can't leave that as your answer because we're talking about the population of wolves, right? So the population of wolves, if you have a little portion of one, then you have one. So 1765 would be your answer. No way to have 0.58 of a wolf.
1066.
Or of a person for that matter.
E. And then it'll be, alright, 0.42. And then times 12. Okay, yeah, I got that.
Everyone got 1765? See how to use that? We're good? Okay.
I need to write this one down.
Okay. Then next, we're going to do a prime example or a classic example of exponential functions and actually teach you something from personal finance. Have you all had personal finance yet?
Yes.
You have personal finance?
I'm taking it.
Right now?
Yeah.
Have you had personal finance? Not yet? So we're going to talk about compound interest.
We did not learn that.
You did not learn compound interest? Oh. Albert Einstein said compound interest is the most powerful force in the universe. And it is unbelievable. So it'll teach you how to make some money.
To be honest.
Oh, okay.
1764.5 aka 1765. Nice.
We're gonna do homework time.
Yep, this is the last thing I'm going to cover right here. Okay, here's an example, real life example of the exponential function. All right, and it's called compound interest. It's in finance. If you can truly grasp this concept, you can have your money work for you and make quite a bit of money. Here we go. So the formula is this: A equals P 1 plus R over N to the NT power. And it's exponential because we have that little exponent, right?
P and a 1 plus, what's that, R?
R over N.
R over N and an NT.
Yes.
Okay.
So we have to know what each letter stands for. So A is going to be your ending amount.
Okay.
So your amount after a certain amount of time. So T stands for time, and we're always going to use years. So if I say we're going to save money for 2 years, T is 2. What if I say we're going to save money for 6 months?
Half a year.
Half a year, 0.5. What if I said we're gonna save it for 1 month?
0.1.
1 over 12, which is like 0.083. So 1 over 12. So you always use time in years. And then we have P, which is your principal. Now in money, the principal is what you're starting with. Your starting amount. Okay? And then R is going to be your rate. So for instance, if we say we're going to save money at 7%, what decimal is 7%?
0.7.
No, that's 70.
Or 0.07.
0.07. Always change your decimal to a percent. Okay? And that's what R is. Now, of this part, you have control over principal, okay, because you can save money and put money away, whatever. You have control over time, in other words, doing it earlier as opposed to doing it later. Like my sons are starting to save when they were 4 and 5 and 6 years old. Where does a 4 and 5 and 6 year old get money?
Us.
Birthdays.
Birthdays, grandma and grandpa give them $5. Or my mom and dad were big on you get a $1 for every year you were born. So on the first birthday I got 1, the second birthday I got 2. By the 18th they get 18. I'm like, Dad, I'm 53. Where's my money? He stopped doing it at 21. I'm like, you're a cheapskate. So they would always get money for whatever, and then they would. My parents lived out of town, so they would send them money to go buy a gift. I said, well, you can spend half of it on a gift, but the rest of it's going in the bank. So you have kind of time, how early you're going to start, and then of course rate is the big one. How many have a savings account? Savings account? Savings account? Do you know what your savings account currently is getting?
No.
What rate your current savings account is? I know what Commerce is. Commerce currently is 0.01%, which means if you put $1,000 in the bank in 1 year, they're going to say, thank you for having your money with us, here's $1. Okay, so it's not a lot of money. Okay, it's going to be 0.01. If you go to like an online bank, like an Ally or a SoFi, where you do everything online, right now they're giving you 5%.
5%?
Yes. Which means if you have $1,000 in the bank, in a year's time, they say, thank you for having your money here, here's $50. Not 1, here's 50. Okay? Big difference between those two. Okay? So when it comes to saving money, we want to make sure our rate is as high as possible. Okay? So the way this works is you take the information, you simply plug and check. Okay? So what letter have I not told you about?
Ending amount.
Ending amount is A.
The end.
I haven't told you about the N.
I thought you meant.
Yeah. I haven't told you about the N. And the N is compounding. Okay? Do you guys understand the concept of compounding, what that means? Have you heard that term before in finance?
Like putting together?
Kind of. Have you heard of compounding,
Nah.
Cordell? Okay, so here's what happens. Let's do really easy numbers, okay? Let's say we have $1,000, and let's say we do it at 10%. We put it in the money, we put it in the bank, and we're getting paid 10%, which is unheard of. I mean, 5% for an online is actually really, really good right now.
Yeah.
Well, let's just say we're getting 10%, $1,000. So you put it in January 1st. January 1st, you make the deposit of $1,000. Okay. So typically, if we are compounding yearly, where n would equal 1, you get your money one time a year. So that would mean January 1st of the next year, they give you your money. So you get 1,000, 10% of 1,000 is 100. So you would now have $1,100. What if I decide to pull it out though in July, after 6 months? How much would I get? After a year, they're going to give me 100.
700.
No. After 6 months, they're going to give me
50.
what's that? Yeah, well, 1050. I have 1,000, they're going to give me $50. Here they gave me 100 after a year. Here they're going to give me 50. We could do this all the way through. If I'm going to pull it out in, let's say, October, that's 3/4 of a year, they would give me 75 and so forth.
Right.
Okay? If I don't pull it out, they're not going to give me the money until January. All right? So let's say it's compounded though let's say it's compounded quarterly, which most of your accounts probably are quarterly. So that means they're gonna give you your money every 3 months. Okay, so January 1st, I put in $1,000. We have January, February, March, so April 1st, they're gonna give you the amount of money they owe you, and they owe you $25. Okay, so they're gonna give you $1,025. Okay, so it's in their April, May, June. July 1st comes along. They're gonna pay you what you're due. Now, what do you do? Another 25, right? Except they don't compute off of this. They compute it off of this. So they give you 10% of $1,025. So now it's not 25. What's 10% of that? Just a little bit more than 25. Oops. So now, sorry?
My bad. It's like 100 something.
It's actually just a little bit more than 25. It's because it's still, I mean, 10% of $25 is very little.
Right.
So it's $25.63. So now you have 1,050, 63, you have a little extra. Okay? So when July, August, September, so when October 1st rolls around and they compute they give you another 25, well, no. Now they're giving you interest on the interest that they paid you. Okay? So now they have 1,025.63 times 0.1 divided by 4. Now they're giving you yeah, 25.64. Because all you got was a little interest on that top one. So now you have 1,000.
I got 25.62.
Oh, you know what? No, that's right. It's 25.64.
Yeah.
So now you have 76.27. Rather than 75, you have a little bit more. Okay? The same thing works. This is what's compounding. They're giving you interest on the interest they've already paid you. Okay? So money you haven't earned is just you put your money in there. Now what if they did this every month? Every month they gave you your money and then they gave you interest upon that interest upon that interest. Okay? What if this was more than 1,000? I mean, this isn't very much. We're talking pennies here.
Yeah.
But if this was more money, like 10,000 or 20,000, you could be making a pretty good chunk of change with compound interest. And it's going to build over time much faster. So let's see, quarterly would be 4. What would monthly be? What would NB equal if we were compounding it monthly? How many times a year would you get paid? 12. So quarterly is 4, yearly is 1, monthly is 12. So as we give you different ones, semi-yearly, that would be 2. Okay. So it's giving you interest upon interest upon interest upon interest. And you do this over several years, it builds up much faster. In fact, you make more money at the end than you did at the beginning because you're interest on interest. By the way, this is also the exact same way credit cards calculate how much you owe them. So if you borrow money and you don't pay it off on the credit card, you just pay the minimum, they charge you interest. The next month you pay interest on that interest you already paid. So they calculate exactly the same way. With the power of compound interest. Okay, so let's do an example of this. Actually put in numbers. So let's say you start off with, throw out a number. Give me a value. How much money you got in your savings, or just give me a random number?
$767.
$767. Outstanding. I'm sorry, that's your principal. That's how much you start with. Principal. All right. And let's say our rate is going to be something like 1%. 1%. And let's say typically it's compounded quarterly, so n is going to be 4. Okay. How much will that be worth in, let's see, you have about a year and a half until you graduate, right?
Mm-hmm.
Okay, so let's go, time is 1.5. How much would that be worth in 1.5 years? If you do nothing else, if you add nothing else to it. You just let it sit. So A equals P 1 plus R over N to the NT power. Okay. So you simply plug and chug. This is simply a plug and chug problem. 767. What do I put in for the rate?
1.
I don't put in 1. What's the decimal?
Oh, 0.01.
0.01. So 0.01 over quarterly to the N times T. So I'm just going to put in 6 power. Because 4 times 1.5 is 6. And then you just plug in the calculator and get your answer. I hate to tell you, that does not make you rich.
778.577.
778.5, and it's money, so you run to the nearest penny.
Right.
So 58
So
cents.
58 cents.
So wow, we made $11.58 in a year and a half. Is that good or bad?
Bad.
What's inflation currently, do you know?
It's 2.5%.
It is. It's typically right around 3%.
Yeah.
You want to keep it around 2% to keep
Right.
things moving forward there. You don't want to go too fast. So if you're getting 1% in your savings account and inflation is growing 2.5%, are you losing or making money?
Losing.
You're losing a point and a half, percentage and a half every time you have money in savings.
Right.
I always encourage kids, if you have a savings account, great. It's safe, it's secure. But if you can find someplace else where you get a better rate, definitely jump on it. That's where personal finance class should come in. They should be telling you about other products
Well, I'm
out
learning
there.
about this now in my college class, not in high school. It's just-
Yeah, I have a savings account and it gives me like 0.002% with however much is in it. So I get like 8 cents a month just from having money in my account.
8 cents.
And at least I'm getting something. It's better than nothing.
Or, unfortunately, your purchasing power is going down. If you moved it to, I think SoFi, I've got SoFi right now. If you don't mind me pulling on my phone,
Yeah,
Are you
no,
offended?
I'm perfectly fine.
I can pull this out and I can tell you what SoFi is right now. How many of you are comfortable doing things online, financial stuff online? I do almost all my bills stuff online, and I'm old. SoFi right now, if you had your money at SoFi rather than making 0.002, let's see, where's my savings? You'd be making 4.5%. So rather than 0.002, you'd be making 0.45. So quite a bit more, as long as you're comfortable doing things online. So it's just where you have your money is important, and compounding just proves that. All right, but that would be a real life example of our exponential function. And then of course we see the graph, right? Okay, this is where you make your growth when it comes to money that you don't make currently. That's where you make your money. I made more money in the past 2 years with investments than I did in the first 15 years. Because this is where I am in saving money with the end tail. So the longer I can hold out, the more growth I'm going to see. That's the power of compounders. All right, I'm done with 22A, so time is yours. Give me a chance to work on what you saw, like 35 minutes.